To introduce the concepts of linear inequalities in two variables, we should begin with a quick review of linear inequalities and equations in one variable. To graph the solutions to the equation x equals 3 on the number line, we begin by setting up our number line with arrows on both ends and by placing a scale on the number line. And we recognize the solution to the equation x equals 3 is 3. And the way we would graph this on the number line is just by putting a solid circle at 3. There is only one solution to this equation. In contrast to the equation in part A, the inequality x is less than 3 in part B will have an infinite number of solutions. To graph that inequality, we again begin by setting up a number line, drawing the arrows, drawing the scale. But the difference is, having an inequality saying x is less than 3 means any x value less than 3 will be a solution. So anything to the left of 3 will be a solution. One way we can represent this on the graph is using the parenthesis at 3 and then shading everything to the left. Another option that people use, instead of using the parenthesis at 3, is to instead put an open circle at 3. The open circle indicating we do want to go up to 3, but we don't want to actually include 3 itself. But we still shade to the left. And in contrast to a less than, a greater than, such as x is greater than or equal to 3, indicates we still want to involve the number 3, but we want to now include it as a solution, and we want everything to the right of 3. So one method is to put the square bracket at 3 and shade everything to the right. The other option people will use is to put a closed circle at 3 and shade everything to the right. The greatest difference between the equation in part A and the two inequalities in part B and C is that the equation had exactly one solution, 3. Whereas the inequalities had an entire half of the number lines being solutions, and possibly 3 itself was or was not a solution. When we deal with linear inequalities in two variables, we're going to have the same sort of situation, where half the graph will include solutions, like the inequalities here did, and perhaps the separation between the two sides of that graph may or may not be included as solutions. We'll now look at our first example of a linear inequality in two variables. Every question in this part of the example will relate to the inequality y is less than or equal to negative 1/2 x plus 1. And because we are now dealing with two variables, x and y, solutions to this inequality must include both an x and a y coordinate. To check if 2, 0 is a solution for this inequality, we follow the same process we would have done had this been an equation. We substitute 0 in for the y, and we substitute 2 in for the x. And we ask ourselves, is this actually true? Is 0 less than or equal to negative 1/2 times 2 plus 1? Well, we follow through like we would in any other example. Order of operations, negative 1/2 times 2 is negative 1, and negative 1 plus 1 is 0. And so we obtain the statement 0 is less than or equal to 0. That is a true statement, so this does check out. And we can confirm, yes, 2, 0 is a solution for this inequality. In part B, is negative 2, 2 a solution for the same inequality? To check, we follow the same process. We substitute 2 in for the y, we substitute negative 2 in for the x, and we try to confirm whether or not 2 is actually less than or equal to negative 1/2 times negative 2 plus 1. On the right side of the inequality, negative 1/2 times negative 2 is a positive 1, and 1 plus 1 is 2. And so we're trying to figure out, is 2 less than or equal to 2? Again, that does check out. Part C is 0, For part C, we need to check if 0, negative 4 is a solution for this inequality as well. Again, substitute the y value for the y variable, and we want to check, is negative 4 less than or equal to negative 1/2 times 0 plus 1? Again, simplifying. Negative 1/2 times 0 is 0, and 0 plus 1 is 1. So the question is now, is negative 4 less than or equal to negative 1? That again is true. For the final ordered pair to check, is 4, negative 1 a solution for this inequality? We again substitute negative 1 for the y, and we check, is negative 1 less than or equal to negative 1/2 times x, the 4, plus 1? Well, negative 1, is that less than or equal to Negative 1/2 times 4 is negative 2, and negative 2 plus 1 is negative 1. So negative 1 is less than or equal to negative 1 is again a true statement. All 4 of these points did end up being solutions to this inequality. So for part E, we're now supposed to plot any of the ordered pairs that were solutions to the inequality. As always, we'll begin by properly setting up our axes. We'll draw the axes using a ruler. We'll add arrows to at least the positive ends of the axes. We'll label the axes X and Y, and we'll put a clear scale on each axis. For this example, I would use a scale of 1, 2, 3 on both axes. We'll now plot the 4 points. Point 2, 0, the point -2, 2, the point 0, -4, and a point at 4, -1. It should be clear from the work that we have, these 4 points do not all lie on the same line. Perhaps, though, this is not surprising. Since we know we're dealing with an inequality, we know the solutions will take up half of this entire graph, just like they took up half a number line when we only had one variable. If we go back to the original inequality we had been given, and think about what if this had been an equation and not an inequality, hopefully we notice this would be in slope-intercept form. With a -1/2x plus 1, I know that my y-intercept for this line would be at 0, 1, and I know my slope would be a -1/2, which would tell me down 1 to the right 2, down 1 to the right 2, or conversely, going up 1 to the left 2, up 1 to the left 2. If we draw that line based off the slope-intercept form of the equation on top of this graph, we'll start to see where the separation is between the half of the graph that has solutions and the half that does not. We'll add the arrows like we always do, and notice that 3 of the points did fall on the line, while the 4th point at 0, -4 did not. By having that additional point down on 0, -4, that's telling us this is the half with the solutions. If we were to pick any other point down here, say 0, 0, or -2, -1, or anything else, 2, -3, all 3 of those points would come back as solutions for this inequality. So just like on a number line, where we would shade half the number line, on this graph we need to shade half the graph. To indicate that the lower half of the graph is the half with the solutions, we'd simply take our pencil and shade in as best we could that side of the graph. This represents the same idea as shading half the number line, except in this case we have a two-dimensional graph, so we need to shade in half of that graph.